One.
Alright, lesson 312 is going to take us to the functions. Going from equations to functions, we find they're very similar. There's just some slight differences. So, start with, you can read all this, but basically I'm going to hit the highlights here. Recall the graphic equation such as y equals x plus 1 is the complete set of solutions for that equation, right? That's the line. The values for y are the result of the process being done to x. In other words, we're taking x up here and we're adding 1 to it. That's the process. And the result is the y. Okay? So that's, again, it goes back to independent and dependent variable. X being the independent variable and y being the dependent variable. So when we talk about functions, we're talking about a process of only one variable that ends up giving you the other. Okay? A lot of times they'll write this in what's called function notation. Okay? And that's actually what this is right here. Function notation. Okay? So that's rewriting it as a function f of a certain variable. We're doing a process with a certain variable. So the process f is a function. In a function, every element, this is super important, every element of the domain is paired with exactly one element of the range. Okay? Every x value goes to a single y value. Okay? You can have multiple x's that go to the same y, like 4, 2, and 3, 2. But what you can't have is the same input, so say 3, go to 4, and then go to 5. So like 3, 4, and 3, 5 would not be a function. Okay? The example I give every year is if X is the person and Y is the month they were born in. You know, person A, right, Jeff, was born in March. Bobby was also born in March. That's fine. You can have two different X values, two different people that have the same Y value or born in the same month, March. What you can't have is Jeff, the input, right, having two separate outputs. In other words, being born in March and July. That's not reasonable. That's not possible. Okay, so that kind of gives you an idea there. So so you got one input, right? The input only has one specific output in the range. That is for every value of x, there's exactly one value of y. Both y and f of x are the same thing. They represent the outcome of the function f onto x. So for the equation y equals x plus 1, adding 1 to x is the function. Therefore, f of x is x plus 1, and y and f of x are the same thing. So basically what we're going to get into is function notation, which would be f of x equals x plus 1. All you really need to know is it's writing the equation instead of x and y. We're writing a function of the variable x. Okay? But it still works the same way, still graphed the same way. Alright? You can be f of x, it can be g of x, it can be r of x, it can be any letter, it doesn't have to be f out front, but it's a function of x, okay? It has to pass the vertical line test. In other words, if you draw a vertical line through it, it crosses twice, it doesn't pass. It has to be 1-to-1 or a many-to-1 relationship. If it's 1-to-many, don't worry, that's like same x going to two different y's, and then if it fails the vertical line test. All right, we've already been through this, writing a function. If you got y equals, what this allows us to do is have two separate functions. We can do it, the first function is f of x, and the secondary function is g of x, and that would be a system. We just spent a whole unit talking about systems. So we're going to continue that with this set notation and with this function notation. Okay? Pause this and feel free to read more of it. And lastly, if we're looking for where the functions cross or where they're the same, then we're looking for where f of x equals g of x. And we'll do a lot of that as well. Okay? All right, some key concepts. Again, you can reread through those. I'm not going to stop and talk about them because they were in the early introduction. And then some more continue. You can, again, pause and write those down if you want them for your notes. And then here's the example. So, talk about points of intersection. Here would be an example of more than one. Linear, which is what we just worked on, has a single point of intersection. And then sometimes we have no points of intersection. That would be like the last one here. Okay? So in other words, both points of intersection are solutions. There's only one solution, and then here there's no solution. All right? And then some more key concepts. Again, pause it. It's just some helpful hints there. Pause it again if you need more, and then we're going to go to the examples here in just a second. Okay? All right, so example 1. Use the graph to approximate the solutions for the following system. Find the difference in outputs, f of x and g of x, for your systems. So, we can see it. It's between what two numbers? I'm hoping on the x values you'll see it's between 3 and 4. All right, so what we want to do is do a little table with those. So I want f of x, g of x, and x, and then f of x minus g of x. All right, so we're gonna do a little table here. So how about we want to do? Let's do. We'll just do 3 and 4. All right, so we want to do 3 and 4. So for f of x, if I go out here to 3, I go up to f of x, it looks like we're talking about maybe 2.5. And then if I look at g of x, go out to 3, we're looking at about 3. Okay? So that'd be 0.5 for f of x minus g of x, actually negative 0.5. All right? And then for the next one, for the f of x, it's going to be at about, at the 4, it's going to be at 3. And g of x is at, it's like 1. So when we subtract that, we get a positive 2. In other words, what we want to realize is where we swap from positive to negative, which is somewhere in between those, is where you're going to have an intersection point. Okay, and like I said, the best estimate we can do for this is somewhere around 3.1 or 3.2. Okay, I'm going to stop this one there, and we'll go from there on the next example.